Dear friend, I am here with you to discuss a very interesting example for the calculation of deflection at point B of a cantilever beam which is subjected with a triangular loading. This is the triangular loading. Or you can say it's a linearly varying loading. The value of load at point B will be 0, and at the fixed end of this cantilever beam will have a value which is W. So value will be ranging from 0 to W. And we are going to find deflection for this cantilever beam using conjugate beam method. This is lecture 7 of module 2. In my previous lecture 5 and lecture 6, for the same module, I have calculated deflection delta B of the same cantilever beam which is subjected with a triangular loading, but by another method like unit load method and moment area method. If you see in lecture 5 for module 2, same problem statement is here. Beam is cantilever beam, length of this beam is L. We have derived deflection general expression for delta B at tip of this beam, which is subjected with a triangular loading. Maximum value is W, but using unit load method. Therefore, now we can see the preview of this lecture using unit load method. At the end of this lecture, we have found deflection delta B calculated was WL to the 4 WL to the power 4 divided by 30 EI. It is the calculated deflections at point B of this cantilever beam. Now, using lecture 6, you can also see the same example which was solved using moment area method. This is a moment area method. Problem statement is same, length of this beam is same, loading is triangular loading, or you can say linearly varying loading. Maximum value is W at the support, and which was solved through moment area method. And you can see the preview of this lecture. I think at the end of this lecture you will see the value calculated for the deflection at point B of this cantilever beam is here. Here WL to the 4 divided by 30 is same value we have calculated using moment area method. Now we are going to solve the same problem and deflection delta B using conjugate beam method. Now let's proceed with the conjugate beam method for triangular loading for this cantilever beam at point B for deflection calculation. You can see the problem statement is here. This is the loading acting on this cantilever beam. The length of this beam is L and fixed end is designated with A and free end is with B. Maximum value of loading is W. And this is the triangular loading. You can say linearly varying loading. Triangular loading. And we are going to find delta B. This delta B using conjugate beam method. Conjugate beam method. As you know, the procedure for conjugate beam method to evaluate deflection at any point for a beam which is subjected with any kind of load, maybe point load, uniformly distributed load, triangular loading, and trapezoidal loading, you need to develop a conjugate beam of a real beam. This is the beam which is our subject of analysis, so it's a real beam. It's a real beam. According to the theorem of conjugate beam method, we need to develop another beam which is imaginary in nature, and we should know how to develop a conjugate beam from the real beam. As per the statement of conjugate beam, any real beam, suppose this is the beam, it's a real beam, fixed end is A and free end is B, its conjugate beam will be free end will become a fixed end. This will be a fixed end, and fixed end will be a free end. So you can say point A will and B will be same, but its support end will be changed. Free end become here fixed end, and here the fixed end for the real beam become free end. This is a real beam. This is the fixed conjugate beam, or you can say imaginary beam, conjugate beam or imaginary beam. Loading pattern in this conjugate real beam is here triangular loading. This is the loading pattern. The length of this beam is L. Here also the length of this beam will be same. And as per the statement of conjugate beam method, deflection is delta B. Here will be deflection delta B. Deflection in real beam delta B at point B will be same as the bending moment at point B of this conjugate beam. If we are able to find bending moment at point B of this conjugate beam, delta B will be MB, where MB is the bending moment. You can write here delta B is the deflection at point B of real beam, and MB is bending moment at point B of the conjugate beam. So in order to develop bending moment at point B, at this point B, we need to find a loading pattern on this conjugate beam so that we can find a bending moment. Otherwise there will be no bending moment at this point B. And as per the statement of conjugate beam theorem or method, the loading bend M over EI diagram of this real beam, which will be directly put on this conjugate beam to make its loading diagram. So in order to solve through conjugate beam method, we need to develop a moment diagram. Then after we need to find a M over EI diagram, and M over EI diagram for this real beam will be put on this conjugate beam to make its loading pattern. After developing a loading pattern on this, we will find out bending moment MB, and calculating MB of this conjugate beam will directly find delta B of this real beam, which is the subject of analysis, calculation of delta B. Now we are going to find bending moment diagram for this real beam, which is subjected with a triangular loading. Now this is the real beam which is subjected with a triangular loading. And length of this beam is L. Its maximum value is W, and its support end is, this one is the support end, which is A, and free end is B. So here we are going to develop bending moment diagram of this, and after that we will develop M over E diagram of this real beam. This is the real beam. Real beam. To draw a bending moment diagram, we need to develop a general expression for bending moment at any section X. At any section which is at a distance of X from point B. So let us say a section XX, which is at a distance of X from point B. Now we are going to find a bending moment at section XX, which will be of this nature, anticlockwise MXX, or you can say bending moment. This is the general bending moment at a distance of X, which is calculated from point B at a distance of X. So we are separating out this part. You can designate this loading pattern here is A, B, and C. It will be a point, you can say it's D, and its point will be E. So we are separating out this loading pattern here. Section X will be same here, and this point is D, E, P. We draw the left part of this section in dotted line for more clarity. This length will be L, and this maximum value which is at support is W. This is a loading diagram. Loading diagram is this. We are going to find loading value at section XX. This value is y equal to ED. We are going to find the value of load at section XX. This is the value of load at section XX. As loading is a linearly varying load, this is the linearly varying load. So load at every section from the point B will be different. So at a distance of X, the loading will be calculated as y equal to ED. So we are going to find this loading from similar triangle method. Take triangle. This point is A, and we have shown this point as C. There are two triangles will be here. One triangle will be this. This triangle is A. This is B. This is C. And there will be another triangle ED and B. There will be another triangle that will be that is D, B, and E. This value is D. This value we are going to find. This is the value of y, and this is the value which is given as W, and this is the section XX where we are going to find the value of y. So from similar triangle, this is the triangle 1 and this is triangle 2. From similar triangle, and this length is L and this length is X. From similar triangle, W divided by L will be equal to y divided by X. Therefore y will be W divided by L into X. So you can see this is a linearly varying load that is y is directly proportional to x. Load is linearly varying with a function of x. So you can say in this expression, if you put x equal to L, the y value will be W divided by L into L. L will be get cancelled. It will be W. So maximum value at support will be W. And this is the linearly varying load. For this linearly varying load, or you can say in triangular loading, we are going to find moment at section XX. So see here, this is the loading diagram in a real beam. This is support. Support is A, this is B, this is C. We have found loading value at any section XX. Right. This is any section XX, which is at a distance of x, and this value we have calculated here. This is y, and we have designated this as D, and this is with E. We have calculated y equal to ED equal to W divided by L into X. We have just calculated here. Here loading is W divided by L into X. This is the value of load at section XX. Now the area of this triangle ED and B will give the total load. Area of this triangle. This is the loading diagram. You can see this is a loading diagram. Area of this loading diagram ED and B. Area of loading diagram in triangle EDB will give total load which will be acting at centroid of this loading diagram. Now the area of this loading diagram will give the total load which will be acting at centroid. This will be the total load which will be acting this centroid of this loading diagram. Now we are going to find out this total load. Total load will be area of this triangle EDB. Area of triangle EDB. Area of this triangle will be half. This length is dB. You can say x, and will be its height ED, which is equal to y, and putting value of x and y will be this one, W divided by L into x. So its value will be WX square divided by twice L. This is the value of this total load. This is nothing but total load, WX square divided by 2L. This is the total load. This total load is acting at a distance of This is a total load, and this is acting at the centroid, which value, as you can show here, this one, x divided by 3. For triangular load, for any triangle, centroid will be x by 3 from section xx. So x bar is x divided by 3. Therefore, moment at section xx, that is our part of calculation, subject of calculation. Moment will be at section xx. This is the moment mxx. We are going to calculate moment mxx, moment at section xx, which is equal to total load. Total load is nothing but this is the total load. Total load wx square divided twice L, multiplying with centroid. Centroid is what? It is x by 3. So moment will be w x cube divided by 6L. This is the general expression for moment for this triangular loading at any section xx, which is at a distance of x from this point B. We have calculated here. Through this general expression, we will develop a bending moment diagram, which is a function of x to the power 3. Now bending moment diagram will be for this triangular loading. This is the triangular loading. For this triangular loading, this value is W, length is L, and this is the load which is acting in this beam. This is the fixed support, and this point is A, and this fixed end is A and free end is B. And bending moment at any section we have calculated here, mxx. For any section xx which is at a distance of x, we have calculated a value as mxx, which is w x to the power 3 divided by 6L. W x cube divided by 6L. This is a function of x to the power 3, so bending moment curve will be a cubical curve. Now, now we need to find the maximum value and minimum value of this one. We are taking bending moment from this point B and we are developing from B to A. So at A, at point B, x will be 0. So bending moment at point B will be mb equal to, in place of x we will put 0, so it will be 0. At point B, x will be L. This is the value of L, length of this beam L. So bending moment MA, moment at A will be designated as a MA. So W divided by 6L, and in place of x we will put L to the power 3. So it will be WL cube divided by 6L. L cube divided by L will be cancelled as L square, and it will be WL square divided by 6. This is the maximum bending moment at point A, or you can say support moment will be WL square by 6, and bending moment will follow a curve which is a function of x to the power 3. So bending moment curve will be here, bending moment diagram will be, this will be the bending moment diagram. This is a function of x to the power 3, and maximum value calculated here is WL to the power WL square divided by 6. Length of this beam is L, and this point is A, this point is B. Now this is the M diagram. You can say bending moment diagram. M diagram. This is the M diagram. Now we are going to develop a bend M over EI diagram. M over EI diagram is nothing but dividing every y coordinate of this M diagram with a constant value of EI, which is the flexural rigidity. So M over EI diagram will be a same curve profile will be same, but its value will be somehow less than this one because every y coordinate is divided by with a constant value of EI. So if we divide this value y coordinate with a constant value of EI, this point will be shifted here, and if there is this point it is divided by EI, it will be here, and if there is a point in this M diagram which is divided by EI, it will shift here. So curve will be somehow less than this value, but profile will be same. So M diagram will be here, M diagram will be something like this, and this is also will be a function of x to the power 3. This is also a function because we are developing from the M diagram, x to the power 3, and this is the M diagram, M over EI diagram, because every coordinate y coordinate of this M diagram has been divided by constant value of EI. M diagram, and its value will be W L square divided by 6 EI, as WL square by 6 is divided by EI, so its maximum value will be WL square by 6 EI. This is the M over EI diagram of a real beam which I have developed here. And now, as per the statement of conjugate beam method, this M over EI diagram for a real beam, M over EI diagram of a real beam will be directly put on the conjugate beam to make a loading diagram in a conjugate beam. So this M over EI diagram will be directly put on conjugate beam. This is the conjugate beam. As I have explained you, this was the real beam and this is the conjugate beam, and we are going to put this M over EI diagram will in the conjugate beam, or you can say in imaginary beam. Now our conjugate beam is, as real beam is here, this is a real beam subjected to this loading, triangular loading, and this is a real beam, and conjugate beam will be free end will become a fixed end, and fixed end will be a free end, and loading diagram for this conjugate beam will be M over EI diagram of this real beam, which will be put here in this same fashion, in the same manner. So it will be something like this, and it will be the loading pattern in this conjugate beam. This is the conjugate beam. This point is A, this point is B, and this point is A, and this point is B, and its maximum value is calculated here, as I have shown you, W L to the power divided by 6 EI. W L to the power 2 divided by 6 EI is the maximum value of loading in a conjugate beam. Now we are done with the loading diagram of this conjugate beam. Now it will be very easy to find the bending moment at point B of this conjugate beam, which will give the deflection at point delta B. Now deflection delta B, which is delta B, delta B will be, delta B in the real beam will be the bending moment at MB in the conjugate beam. Now we are going to find MB is the bending moment in conjugate beam. Bending moment in at point P of conjugate beam. and delta B deflection and B of real beam. Now we are going to find bending moment at point B of this conjugate beam. This is the conjugate beam. This is the fixed end. Loading is this. This is curve is a function of x to the power 3 and loading is here in this manner. Length is L, this point is A and this point is B, and we are going to develop bending moment at this one. So area of this loading diagram will give total load, and total load will be acting somewhere. Suppose this here total load is acting. This is the total load which will be acting at centroid of this loading diagram. This is the total load. This is total load. Total load multiplying with this centroid of this loading will give bending moment MB. Now we are going to find out total load of this loading diagram. For that we need to find the area of this loading diagram. Now area of this loading diagram can be calculated here as this is the conjugate beam. Now conjugate beam is this one. Maximum value is total loading is this is the maximum loading W L square divided by 6 EI, and length is L. This point is A, this point is B, and this is following a function x to the power 3, and from the general expression for any function x fx which is a function of x to the power n, we can say this is the any curve which is a function of x to the power n. If this is the base is b and height is h, area is equal to 1 divided by n plus 1 into b into h. This is the area of this any curve which is a function of x to the power n. Since this is a function of x to the power 3, so from the general expression n will be equal to 3. So area will be from this expression 1 divided by, in place of n we will put 3 plus 1, in place of b which is a length L, which is height as per the general expression h will be WL square divided by 6 EI. This is the height. You can say this is the height and this is B. So it will be 1 divided by 4 multiplying WL to the power cube divided by 6 EI. This is the area of this loading diagram. This is the area of this shaded portion. This is what? This is the area of this loading diagram. You can say area of loading diagram of conjugate beam. This is the conjugate beam and fixed support is here. This is fixed. This is the free end. Low conjugate beam. Conjugate. And this area of this conjugate beam, the area of this loading diagram of this conjugate beam will give the total load. This is the total load. area of this conjugate total area of this loading diagram of this conjugate beam will give the total load of this loading diagram. Total load will be acting at some point here. It will be acting here. This is the total load. Total load will be what? 1 divided by 4 into WL to the power 3 divided by 6 EI. This is the total load. Total load will be at a distance of x. You can say x bar of this loading diagram, or the centroid of this loading diagram. So total load multiplying with this x, or centroid of this loading, will give the moment at point B, which is MB, which will be here MB. So now calculation for x bar. From the general expression of any curve which is a function of x to the power n, x bar is, from the general expression, n plus 1 divided by n plus 2 multiply its base length b. So in this loading diagram, base length is L, so b will be equal to L, and in place of, this is a function of x to the power 3, so n will be 3, so x bar will be, in place of n we'll put 3 plus 1, 3 plus 2 multiplying base length is L, so it will be 4 divided by 5 into L. This is the central distance of this loading. Total loading will be acting at a distance of 4 upon 5 L from support, or you can say from point B. Now centroid of this loading multiplying with this total load. This is the area of this loading diagram. So MB will be equal to total load multiplying with centroid. Total load is here 1 by 4 WL cube divided by 6 EI. So total load is 1 divided by 4 into WL cube divided by 6 EI multiplying with this centroid. This is the x bar, 4 divided by 5 L. We can cancel out 4. Now it will be WL to the power 4 divided by 6 multiplying 5 will give 30 EI. So bending moment at point B of this conjugate beam. This is the conjugate beam. Bending moment at point B of this conjugate beam will give deflection at point B in the real beam. So it will be delta B, as I have explained. So delta B is WL to the power 4 divided by 30 EI, deflection at point B in a real beam. I hope you might have understood the entire procedure for finding out bending deflection at point B, or you can say at free end of this cantilever beam, which is subjected with a triangular loading or linearly varying load. Dear friend, you can also go through